Right. Great. So, thank you. Coming back to the second half. So now we have two more talks. First off is Daniel Grumiller from Vienna, from the
Yeah, thanks. And also thanks for inviting us to my first time in Keynote. It's a bit embarrassing given how close Vienna is. Maybe for a while. And today this is going to be almost entirely a classical Java talk, so very little relation to steam theory. It's based on this recent work with two from students who are not related to the project. So here's the sort of executive summary. The main goal is to understand the threshold of black hole formation. And as you know, stationary black holes are very simple objects. They're fully characterized by video of a handful of numbers, mass, momentum, and charges. But the process of black hole evaporation and formation, they're very complicated processes. And here, the interest is the threshold of black hole formation when we sort of create infinitesimally small black holes, or just the state before a black hole actually forms. And so far, there's only a numerical understanding of this process, and the catchphrase here is trivial collapse. I'll explain what this means. And the goal in our work is to get an analytical understanding of these critical solutions, which have this property of being spacetime crystals. And the key technique that we use is to employ the dimension E as an expansion parameter, because GR doesn't have any dimension as an expansion parameter that it could use. Okay, so I'll start with the definition of what I mean by spacetime crystal, then what I mean more specifically with critical spacetime crystals, and then I'll show you the details of the large T expansion. Here's again more a summary slide, so a brief overview on the specific goal that we want to achieve. So crystals, as you know, are states where you have a spontaneous symmetry breaking of spatial translations. Time crystals is the analog for time translations, and spacetime crystals when you have spontaneous symmetry breaking of spacetime translations. And critical spacetime crystals are discretely self-similar solutions to opportunity. So why are these solutions relevant? Well, this is based on theoretical work that goes back to the 80s by Christopher and to the discovery by Chuck Hewitt using numerical GR. I'll explain this picture in a few slides in more detail. For now, the main message is that depending on the initial data, you get either a black hole as a final state or flat space as a final state. And for infinite fine-tuning of initial data, you get a splitting solution. That's our main solution of interest. So the claim is that at the threshold of black hole formation, the solution is a critical spacetime crystal, and the buzzwords here are critical collapse and four-dimensional Monod vector, and I'll explain this a few slides from now. And this critical spacetime crystal is characterized by universal parameters. So universal means they don't depend on what kind of one parameter family of initial data you started with. And I will define three of them in my talk, but now you can think of them as analogous to critical exponents that you may find in second order phase transitions. Dense matter systems, for instance. And so far, there's no first principle derivation of these key parameters. As I mentioned, the technical issue is that GR doesn't have any small parameter. Moreover, we cannot use any of the other standard perturbation theories that we're familiar with in GR. So this critical solution is not some small perturbation of velocity space, but it's also not a small perturbation of charge vectors. And our resolution is to take the spacetime dimension as a parameter and to vary it. And there are two regimes so we can do perturbation theory in the dimensions. One of which is this large T expansion, which is nicely summarized in this video by so as it will turn out, we can use either 1 over D or D minus 3 as a small parameter. And the key aspect of this approach is to construct directly the critical spacetime crystal, so the solution at the threshold of black hole formation, rather than trying to do a critical collapse. Okay, so let me start now with the definition of what I mean by spacetime crystals. So let's consider discrete self-similar spacetimes. the most convenient way to define them is to use slightly adapted coordinates. So the only coordinate that I'm adapting is tau. This metric G mu is now a discrete self-similar metric, and it's conformal to G tilde, or the conformal factor e to the minus tau. And this metric G tilde is a spacetime crystal in the sense that it's periodic in this coordinate tau with periodicity delta. And delta is known as the plane period. And the assumed vector field in tau, the crystal vector, can be either space-like, then we will have an ordinary crystal, or it can be time-like, or it can be null. And in these critical solutions that I'm going to present to you, this crystal vector actually changes the signature, and the null separatrix between the regions where it's space-like and time-like is known as self-similar rocks, and we will assess the signature. All right, so let me now define for you the space-time crystals. So this is the picture shown on the motivational slide. So if you start from generic initial data, say in the system Einstein gravity plus some matter fields, the simple space being mass scalar fields, then this is supposed to represent some one parameter family of initial data. P is the family parameter, and for some values P bigger than P star, you always form a black hole as a final state, and for P smaller than P star, you always form a flat space as a final state. And so that means by bisection you can approach this critical point P equals P star, where you neither form a black hole nor flat space. And this is exactly the critical solution you're interested in. If you perturb it a little bit, then you either fall into this phasing of reflection or into that phasing of reflection. So this critical solution is an attractive codimension one in the sense that it has one unstable mode, but otherwise all initial data are attracted to it until the unstable mode fits in. So if you do this infinite fine-tuning, if you exactly go to P equals P star, then you have the threshold of back formation, and that gives you the critical solution. And for a certain symmetric collapse of master scales in Einstein gravity, one can show that this critical solution is discretely self-similar. So it is the spacetime crystal because it's a critical solution with the critical spacetime crystal. This solution is characterized by universal critical parameters. The primary observer is the echoing period delta, which was defined on the previous slide, and I'll show you in the picture in the next slide. And secondary observers are the Chapullo exponent gamma, which I'll define in a moment, and the neck angle alpha, which I'll show you in the next slide, just to define what I mean. Good. So the Chapullo exponent is defined as follows. If you're slightly above the threshold of black hole formation, then you get a black hole with some mass. And the mass turns out to scale in this way, P minus P star to sigma exponent gamma. P star is the critical value of the parameter, and you have one parameter family of initial data. P is the parameter of this solution, which is always bigger than P star. And gamma is a pure number, and that number doesn't depend on the family that you choose. So this is this universal critical exponent that has a specific value for any given model. Okay. And another interesting aspect of this solution found by Chapullo is that Hawking lost the bet because of it. Because this critical solution can be proven to have a naked singularity. So it's a counterexample to a very strict form of eccentricity that no reasonable initial data can form a naked singularity, or this is a counterexample. So you need to sharpen your formulation of cosmic censorship if you want to maintain it. So it's still a set of measure zero. So if you throw a random dart on initial data, you will never reach the solutions. In that sense, you can still say we don't care about this naked singularity, but in principle, you could form this by infinite fine-tuning of initial data. And the key idea to get all these critical parameters, delta, gamma, and the technical alpha, is to directly construct a critical solution, because once you have the solution, you automatically get experiments. So you don't have to construct infinitely many solutions and do fine-tuning and come closer and closer to the critical solution. You just directly construct a critical solution. So here's how this critical solution looks like schematically. Here's the naked singularity, and what lights. So lines of 45 degrees are null lines. So this patch here between these null lines is path patch, and in this path patch, this lattice vector d tau is time bound. On this SSH it's null, and in these outside regions it's spacetime. The color coding is that regions in blue have negative Richard scalar and regions that are positive. And these black lines are the lines where the Richard scalar vanishes, and that happens to coincide with lines where the null energy condition separates. And it turns out that these lines always intersect in the origin of space-time. So that means these two null lines meet at a certain angle, and that angle is what we call the neck angle, and that's a diffeomorphism invariant quantity that characterizes this distributed solution. So it's something you can measure in your numerical experiment. This is the same picture as a tenuous diagram. So you have spherical symmetry, so I'm dropping the d-2 sphere part. This is again the self-circular horizon. This is the path patch here. And to construct the solution, it's sufficient to construct it in this fundamental domain, because of periodicity, you know it then in the full path patch. Once you know that path patch, by smoothness, you can continue it outwards into this outer patch, all the way up to this Cauchy horizon. And here's the naked singularity, where the Richard scalar goes up. But it's in some sense a very mild curvature singularity. In any epsilon region of this naked singularity, you find infinitely many points where the Richard scalar actually vanishes. So it's widely oscillating as the amplitude. And here you see again the net angles with the same color codes. All right, so let's now get into the details. This is the model that we are considering, the Einstein-Klein-Gordon model in d spacetime dimensions, size the scalar field, and with some d-dimensional metric that is spherical symmetric. Because of spherical symmetry, we can effectively reduce this to a two-dimensional kiloton gravity model with a two-dimensional metric and some kiloton field that is essentially the surface radius of this d-2 spheres. And the advantage of doing so is that you can treat the dimension here as a continuous parameter. Here you might feel uncomfortable defining Einstein gravity in 3.5 dimensions, but once you have it in this form, well, the dimension is just a parameter in the kiloton potentials. There's no problem with relatively continuing them to any real number, at least real number bigger than 3. Okay, so I show you in detail the gauge fixing, because later I'm going to show you some plots and exact results for these functions. So this is the spherical symmetric metric in d dimensions. G tilde of beta is the two-dimensional critical spacetime crystal that is periodic with period delta. And it turns out to be convenient to use a gauge where we have some over-conformal factor. They will call this function omega. And essential part of geometry is captured by this SSH function f, which takes the value x squared at the self-similar horizon, so that this factor here vanishes. Otherwise, it's different from x squared. And all these functions in the scalar field are periodic with period delta. That's my assumption of this split subscalar. There's some residual gauge fixing, which we conveniently try to set the SSH at x equal 1, so that f of tau and 1 is 1. And it turns out there's an additional residual generalized symmetry, not of the action, but of the equation of motion, which is essentially time translation variance, and it's fixed by choosing the phase of one of the Fourier modes. Okay, before I show you the equation of motion, let me introduce the null projections of the scalar field. So we define these future pointing radial null vectors, v and u, and project the first derivative scalar field with respect to them. This defines first order fields psi plus psi minus, and then the gauge fixed Einstein-Gordon equation states. Well, I say simple, but there's still coupled nonlinear partial differential equations, and it's very hard to find solutions other than using units. So the question is how to solve these equations of motion with some given periodicity and regularity conditions. And well, you can do this numerically at finite values of b. This has been done in the past, and we recently did this for continuous values of D, because we're interested in how, for instance, the echoing period behaves as a continuous function of the dimension. I'm going to show a plot soon. But of even bigger interest to us was finding analytical solutions to this set of equations. And if you stare at this equation, you immediately see the dimension appearing in such a way that you may expect something interesting to happen when the dimension goes to infinity or to 3. And indeed, we find that there is a meaningful large Higgs function where we get analytic, very simple solutions, and this is going to be the focus of those that we talk. I just want to announce that there's also a similar expansion in the limit where D approaches 3 from above, but this is less developed, so this is maybe something interesting for the future. All right, so before I do the large Higgs function here, the regularity and complexity conditions of relevance. So regularity just means we want the Ricci scale to be finite in the center. This implies various conditions. There's also some regularity condition implied from the SSH, which I'm not displaying. And there are various complexity conditions, so you can prove this chain of inequalities. Most of them are by construction, because we demand that the radial coordinate x has 0 value in the center, so it has to be bigger or equal to 0, and the SSH is at 1, so x has to be in the range between 0 and 1. Moreover, f has to be strictly bigger than x in all the region except on the SSH. But the non-trivial aspect is that f is always bounded from above by 1, and you can prove this by analyzing the equations in motion. And this is going to be important in the large Higgs function. That's why I like these conditions. Now, when you numerically solve these equations in motion, you find that the solution is actually unique for each value of the dimension and yields a specific result for the echoing period delta depending on the dimension. So this is based on this work by Grumiller, which is based on this eigenvalue problem. He solved this in 4 dimensions, but the same kind of solution works in other dimensions. So before moving on to the large G analytics, I'll show you some numerical results, and I'll give a puzzle to you, so I'll let you guess the function. At the end of the talk, you can verify or falsify output the x was. It's not that function. So this is our result for the echoing period delta as a function of the dimension in this range of dimension between slightly above 3 and 5.5. And the error bars are smaller than the thickness of this line here. This dot here is the well-known result in 4 dimensions, which we use with high accuracy. And to me, the only sort of slightly surprising aspect was that there is a maximum in this curve at this somewhat random dimension. I'm not sure if this is anything profound, or most likely it's just a random number. But it means, or it suggests that if you zoom out a bit, that the behavior of delta for large dimensions is likely to be that it goes to 0 from above. And also when you approach 3 from above, it's suggestive that delta also goes to 0 from above. And this may explain why these 2 dimensions, d going to infinity, d going to 3 from above, simplify the equations of motion. Okay, so here now the geometric functions, the numerical results for them. So f in blue is this SSH function, and that's the function that I wanted to guess in the large G limit. So for dimension 3.05, it's a rather bland function that just interpolates from 1 and the SSH to something very close to 0 in the center. In 4 dimensions, you see these peaks developing at the origin, and it doesn't go to 0. And these peaks start increasing as you increase the dimension. So in dimension 5.5, the peaks are more pronounced, and also this lower pedestal gets raised a little bit. So your task is to guess the large G version of that function. In try to picture it and save it for later, and in the end, I'm going to reveal it. And let me know afterwards how to do it. The other function is omega, so this conformal factor, and that the main info is it flattens out for increasing D. So for E equals 3.05, the peak is about 4.5. In 4 dimensions, only 0.8. In 5.5 dimension, it's rated up to 0.3 or so. And you can imagine that at infinite dimension, this will just turn out to be very flat. Okay, so let me now go through the large D expansion. So these are the first two equations of motion. And what you can see is that if you want this term and this term to remain finite at large D, then omega has to go to 0 at large D. Because, well, you have to somehow compensate this infinite factor here. And if you do this, then you also resolve this issue here, because you want this to be finite. That only works if d minus 3 times e to the omega minus 1 is finite. Since this small omega has to go to 0 up to 1 over d corrections, it's convenient to define a rescaled quantity, big omega, which is just d minus 3 times e to the omega minus 1. And we also divide by x squared, so that this function here is actually finite for it. Okay, and you could use this expansion parameter 1 over d or 1 over d plus some constant. For comparison with neck input results, it's convenient to use this expansion parameter 1 over d minus 1. So that's what I'm going to use. And then we just tailor expand all the metric functions and scalar field functions in powers of epsilon, starting at order 1. And well, we'll go up to next in order. It's convenient to redefine matter fields as sum and difference of this fields plus and minus that I introduced. And then there's a small subtlety. It turns out that whereas I also has a tail expansion starting at order 1, consistency with the equation of motion demands that psi starts at order epsilon. That's the only mind sign. Okay. So this is the result for the linear model solution, and it's surprising that it's so simple. Usually when you get some non-trivial GR solution that is time dependent, it's either physically meaningless or so complicated that you can't write it in closed form. Here, you can write it in terms of very elementary functions. So what you can see is that there's one arbitrary integration function beta of tau. At this stage, there's no restriction beta of tau. Any beta of tau solves the field equations. And this function appears in all the geometric and metric functions. So it appears in this informal factor function, omega, in the SSH function f, and in the metal fields time psi. Here's some key features. This solution indeed obeys all the parity, regularity, convexity, and convex conditions. It's a correct critical spacetime crystal. As required, it has an SSH at x equals 1. So you can see that if x is equal to 1, then this goes 1 plus beta squared over 1 plus beta squared, so x 1 is required. It also yields the correct neck vertex line, by which I mean, if you look at x equal to 0 and check where's the maximum of f, then you find it's located at series of beta. And these series of beta coincide with the series of pi, which is exactly then the vertex where the two necklines meet. So that's a non-trivial cross check that this matches at least some features of finite critical spacetime crystals. However, the major difference is that the solution is not unique. At any finite D, we find that there's a unique solution. Here we find a continuum of solutions labeled by this arbitrary function beta of tau. Moreover, the echoing period delta is not fixed. Any periodicity works. So that's again a major difference to what happens with finite. And we were slightly puzzled by this. I mean, on the one hand, it's maybe good because if you want to be able to match any finite value of D to some large D expansion, then you should be able to model all possible values of delta that appear at finite D and all possible functions beta that are of relevance for different finite D solutions. Still, we wanted to see what happens if we go to next reading model to see if some of these features change when we do next reading. So I'm not going to show you the next Win order solution explicitly. It's very simple. It's again expressed in terms of elementary functions, but it's not really mean that if I do this, the main takeaways, we get no new integration functions, and we obtain explicit results for all functions. One key detail I want to highlight, when you expand this SSH function to next linear order near the self-similar horizon, close to 0 of beta, then this is what you get. So the subleading term is this epsilon 1 minus x. Then this term beta, beta double prime plus 3 beta prime. The key observation is if this term in parentheses doesn't vanish simultaneously when beta vanishes, that would mean that f has to be bigger than 1 on one of the sides of the 0 of beta, and that would violate our convexity condition. So that cannot be the correct solution then. So that means we get actually a restriction on beta double prime plus 3 beta prime, and you can solve this restriction by fixing the Ekman period. So the key conclusion is that the Ekman period no longer is arbitrary, but it's actually fixed. It's fixed by this ratio of the value at zeros of beta. So that means we get already the prediction for what this Ekman period is from taking the count next leading order. It's no longer arbitrary, but it's uniquely determined once I give you beta. And beta also has to obey this Tamal restriction, because if beta of 0, if there were a different solution to beta equal to 0, then all of them have to give the same Ekman period for instance. So let me just summarize some generic features of solutions to various orders. For leading order, you get the correct neck vertex time, no restriction on the Ekman period, no restriction on this arbitrary function, no bound on the dimension, and the maximum of the function have to stay at 1 for all various levels. And these features here, well, we don't see it finally. Now, for next leading order, turns out you get actually the correct neck vertex time and the correct leading order neck angle. I'll show you a plot in the end. This Ekman period is determined for reasons I just explained. There's a mild restriction on this function beta of tau, but there's still no bound on the dimension. And the maximum of f still remain 1 for all various levels. If you go one order higher, so next leading order, you not only get the correct neck vertex time and the correct neck angle, you also get this characteristic downward bending of the necklines, showing here near the center. Delta is still determined. You get mild restrictions on beta. And now for the first time, you get also a lower bound on the dimension. So for any choice of beta, there's a lowest dimension for which this choice of beta works. Moreover, you find that the maximum of f actually decay in this particular way as you approach the center, which is what is qualitatively observed at final. And if you go to next leading order, which was the farthest we got, then you get not just the correct neck vertex time and neck angle, you also get the corrected, you get the predicted order epsilon cubed corrections that were calculated 1.5 years ago. You get a better approximation to downward bending of the necklines near the center, more restrictions on beta, tighter bound on the dimension, and corrections for this decay of the maximum of this SSH. So the upshot is that including higher orders makes the solution more realistic and more constrained. And we take this as a positive signal that maybe this large D expansion is something that makes sense in the sense that the higher you go in the order, the more realistic the solution gets and the better approximates solution that final values. We picked a very simple example just to produce some thoughts. By simple, I mean we pick the minimum number of Fourier modes that works. If we just take one Fourier mode, turns out that it cannot work. You can never obey this next to leading order condition that the zeros of beta coincide with the zeros of 3 beta double prime plus beta prime. So you need at least 2 Fourier modes, and since we wanted to keep it simple, we just took exactly 2 Fourier modes. We fixed the Ekman period to 1, just for simplicity. And then it turns out to obey this next leading order constraint, you have to choose this amplitude here in a very specific way. So this is no longer free, but it's determined by a time period. And we evaluated now this solution using our analytic results up to next anymore. Now you can recall the function that you memorized, your guess for this function f there with the plot. So these were the results of finite dimension. This is the result for dimension 300 with this instance. So was this more or less consistent with this? Okay. So yeah, this is the exact analytic large T result, and these are the final T results. This for this function that looks very reasonable. Okay. The final plot I want to show is the result for the necklines and the various orders. So for leading order, as I mentioned, you only get the neck time correctly, but you don't get any neck needle. But already to next to leading order, things look better. So you get this triangular shape here, the green lines, and the angle here is indeed exactly the correct large mean neck. Now, to next leading order, you see that these lines are no longer straight, but they bend downwards, which is what we find in the numerical results as well. And to next leading order, the downward bending gets further pronounced. What this suggests is that the large D expansion may converge more rapidly in the center than at the SSH. And this is these plots are for this example up here with dimension 300. Okay, so I'm already in the last slide. So not sure how much time.
About 5 minutes.
Okay, good. More time for questions, so I use 5 minutes on the slide. In principle, we could push the debate whatever the expansion beyond next to leading order. It gets a bit tedious. I mean, the number of terms that you get increases exponentially, so it's a bit like going from a 3-loop calculation into a 4-loop calculation. We don't have a strong incentive for doing so. But it would be interesting to understand would we get more constraints on this function beta and on the dimension p. It's conceivable that as you're taking into account more and more corrections, you get more and more constraints. And ideally, if you're taking into account all corrections to all orders, maybe you get a unique result for this function beta for any given dimension p. Another question is, does this perturbative series in 1 over D actually converge, or is this an asymptotic series? We don't know. On the numeric side, it would be interesting to push the numerics beyond equals 14, which is the current upper limit. And the reason why this would be useful is because we have this conjecture that the limit of D going to infinity of the second period goes to 0 from above. And not only that, for this large D expansion, it's actually kind of important how delta goes to 0. For our work, we assume that it goes to 0 in a way that is not monomial of this type here. But if delta goes to 0, like d to the minus 1 over n for any integer n, then you can show that this perturbative series gets reshuffled and the subleading corrections get modified a little bit. And how they get modified depends on the integer value n here. So for this reason, it would be very interesting to find out how the Eking period goes to 0, if indeed it does goes to 0, and that's only possible if we go to considerably higher values of E. So the big challenge is to find some numerical recipe that allows you to push these numerical simulations beyond the current equals 14 to much higher values, like equals 100, 1,000, 10,000, or even much higher than that. In both the numerical and the analytic work, we constructed a solution only in the fast patch because that was sufficient to get the Eking period, the lag angle, and also the periodic exponent gamma. But it might be interesting to extend this solution to the outer patch, all the way up to the Cauchy horizon, and then to consider if or how you can extend beyond the Cauchy horizon. So in 4 dimensions, this was done by, I think, Garcia and Hunder. But in higher dimensions. Another open task is to derive the Chapleau exponent gamma from linear perturbations around the critical spacetime crystals. This is how you get generally the Chapleau exponents. You take the critical solution, you analyze the linear spectrum of perturbations around the critical solution. You find as one unstable mode. You calculate the Lyapunov exponent numerically, and the inverse of the Lyapunov exponent is exactly this critical exponent gamma. And there is an expectation in community that gamma tends to 1/2 with t goes to infinity, but nobody was able to show this analytically. So this is what was very interesting to do. Perhaps using our analytic results for this large T solution for critical spacetime crystals as a starting point. I talked only about large D in my talk, but I mentioned there's also small D minus 3 expansion, and this is far less developed, and I think it might be interesting to develop it not just for the purpose of critical collapse, but more generally. The large D expansion, championed by Roberto Emperon and collaborators, has found many applications in GR. So not just restricted to critical collapse, and it could be that there are also additional applications for D minus 3 expansion. So yeah, it would be interesting to develop. Yeah, moreover, once you know that large D expansion is useful in the context of critical collapse, it might be interesting to go beyond spectral symmetry or to consider different method that are just master spanning all model. There was also recent work by Clark and Pimentel, where they did a large D analysis of a very similar system, so Einstein gravity in a large number of dimensions, spectrally symmetric, but with perfect fluid matter, and they focused on continuously subsimilar solutions. It would be interesting to see if there's a relation to that. More speculatively, since there's a naked singularity, at some point when you come to close the naked singularity, you can no longer use the supergravity approximation. You have to take into account single clustering or quantum corrections. And recently it was argued by Mansevich and Fu that this single clustering correction suggests that this discrete self-singularity is anomalous. Yeah, that there is actually a mass gap once you take into account back corrections. And finally, to make at least one attempt to connect to the topic of this conference, this critical spacetime crystals have naked singularities. And well, it's interesting to find out how singularities are resolved, for instance, within string field. And yeah, let me stop there. Thank you.
We have some time for questions.
Since string theory says that the maximum space-time dimension can be 10, how does this fit, this large D analysis fit in this?
Sure. I mean, the way I think about this large D, even though it's, well, it's an analogy, but it's similar to the large N limit in Young-Mills. So if you're interested in QCD, then you may doubt whether large N is useful because 3 is really not a large number, but for some observers, it turns out to be useful to get a large N approximation there. So I think about it in a similar way here. Of course, we're interested in dimensions that are smaller or equal to 10, whatever. But we can still gain some analytic insights if we use large D expansion. So it just, in some cases, it reduces the complexity of the problem enormously.
For instance?
Yeah, so there is a series of papers by Roberto Emperon where they consider various applications of large D in generativity. There's this effective soap bubble model of the black hole that they came up with. And the equations that describe this bubble are considerably simpler than the full-fledged GR equation. So some problems that require the order of 100,000 CPU hours and then hardcore numerics can be solved in 2 lines of Mathematica, and it runs for 10 minutes. And then you get the solution. So that's the level of simplification that you can achieve. It gives you at least a very good qualitative insight of what is happening, because numerics is great, of course, but it's also a bit of a black box, right? You give in some initial data, on-way data, and then you get some output, but you may not be able to discern what is sort of the gist of the fact that you want to describe. Why does this happen? And we have a similar motivation. I mean, of course, the numerical sounds quite Chapulek for dimensions. That's all great, but we want to understand why is the echoing period 3.44, whatever, and why is the Chapulek exponent gamma 0.36, and so on. And to get insights, we take this large D expansion, and the goal is to determine this critical exponent gamma and the echoing period by some analytical methods to gain a better insight into critical gaps.
Are these critical spacetime crystal solutions known for higher degree interactions? Like if I go beyond GR, does anyone know that the solution still exists or can we follow it?
Not that I'm aware of, no. I don't think that was considered. So people consider GR with various matter content, muons, fluids, complex data fields, etc., etc. But I don't think they've considered to find corrections to G time. So yeah, it might be able to be considered, but was not considered.
Any questions? No, that's the thing coming up.